Hello, my name is Cohort Lahban, and I am part of the Carnegie Mellon University's Robotics Institute Scholars Program. I will be discussing on tuning mechanical and aerodynamic properties of micro-whisker sensors for improved airflow detection, inertia, drag, and direct contact sensing. Whiskers, also known as vibrissae, are important features for mammalian sensing. Mammalian whiskers have inherent properties which allow them to be useful for a selection of different stimuli. For example, seals can use their whiskers to track flow and detect their prey without using their visual senses. Also, mammals such as cats can also use their whiskers to be able to navigate in the dark and the surrounding. Over the years, engineers have made several attempts to replicate these similar properties of whiskers into mechanical devices that can perform with similar characteristics. At Carnegie Mellon University's Microrobotics Lab, a model has been developed that replicates these exact properties of mammals into configurable devices that can similarly detect stimuli without any optical dependencies. The WhiskSight sensor. The WhiskSight sensor has a fixed design which can take in a configuration of arrays of magnetically attached whiskers into elastomer membrane, and we use a camera as a single interface to track flow. Performance of the whisker sensors is important for several of its properties: the elastomer material substrate, the shape of the whisker array, and properties of the whisker under flow conditions. These properties are important to understand how the whisker performs under different flow variations and the information received from the whisker. We perform several experiments to better understand the whisker behavior when flow is applied. We use commercial devices such as a fan to apply flow to our WhiskSight sensor to track flow under different conditions using different materials. When flow is applied on the whisker, airflow moves from a point of zero to a point where airflow begins and where airflow is stable and starts decreasing as flow is removed. The distribution on the right shows the flow trajectory of airflow within a time interface of 0 to 20 seconds. When flow is applied, the whisker moves simultaneously from one point to the other. As you can see, the whisker deflects from point A to point B. We also use a computer vision algorithm to track the whisker behavior. The dark dots represent potential whiskers, and the arrows point towards the direction of the whiskers. Investigating on the material properties of the whiskers, we use platinum catalyzed silicon, also known as Aeroflex, at different thickness to test the behavior of whiskers under different flow speed. The difference in material thickness and its responsiveness to the whisker performance when airflow is applied is determined by the difference in their Young's modulus. We observe these properties by testing the different whiskers and observing the result. From the distribution, we see that low thicker elastomer responds with greater deflections from the whisker when airflow is applied, while higher thicker materials had lower whisker deflections on the same conditions. Higher thicker materials are represented on the distribution by the red dot, while lower thicker materials are represented by the green dots, and we can see the variance in their deflection values with respect to the flow values. So the distribution is the mean deflection on the airflow against the flow speed from low, medium to high. To summarize this, different elastomer materials will change how the whiskers react to airflow. Material thickness is an important property on whisker deflection when airflow is applied. The results from this study seek to highlight new elastomer properties of airflow which would be of interest. And potential applications of this WhiskSight sensor could be to detect flow in aerial aviation for unmanned aerial vehicles and micro aerial vehicles.